All right, good morning, everybody. Hello, welcome. Welcome back to Discovery Park, to another in our series of distinguished lectures here on campus. And it's really a great pleasure to welcome again Dr. Steve Koonin to campus. He visited us about 2 years ago, and at the time spoke about the work that he was doing at NYU and in New York on advanced technology and the future of urban environments and how to optimize those. Today, the topic is going to be different. We're going to talk about certainties and uncertainties in our energy and climate futures. Okay? And Dr. Koonin is, who better to come and talk to us about these topics. He's had a stellar career. He was the provost at Caltech, and then from there, went on to spending a few years as a chief scientist at British Petroleum, came back from London and became the Undersecretary of Science at the Department of Energy in the last administration, and then from there went on to NYU, where he launched this new Center on Urban, Future of Urban Environments, and now is, over the years, has been extremely active in really taking a good, deep look as a scientist at the questions of climate and energy. So with that introduction, please, Steve, welcome.
Good. Thank you. Thank you, Thomas. It's great to be back, as I said to your president a couple minutes ago. Yet new, interesting dimensions to learn about on this second visit. As Thomas said, I've been involved with discussions of the climate and energy nexus for just about 30 years, and I want to take today the approach of a physicist, namely I'm data-driven, and let's talk about the science and what it tells us and might not tell us about where we're headed in the future. Unusually for a number of fields of science, there is a consensus position on climate science, and that's elucidated both in a set of periodic reports that the UN puts out. The most recent was in 2014. Another one is due out in a couple of years. And then again, the US government, a year and a half ago, put out a science report, and then on Thanksgiving, put out an impacts report, jointly under the name of the US National Climate Assessment number 4. This is the fourth of a quadrennially issued report. And both of these are meant to summarize, survey the state of climate science and the likely impacts of a changing climate under both human and natural influences. One of the summaries of that second report was put out by one of its primary authors, Kathleen Hayhoe, who in a tweet, and you can see this is from August of 2017 when the report became public, the science bit. It's real, it's us, it's serious, and the window of time to prevent dangerous impacts is closing fast. Said a little more formally, it's real is that the climate is changing. That's an issue of detection of a changing climate. It's due to humans. That's an issue of attribution. The impacts we're seeing now, with worse to come, projection, and then we have to act now. So detection, attribution, projection, and response. Now, I and many others read not only the US report, but the UN report and the scientific literature with the eyes of a scientist, both people who know actually something about the science. And when I look at Catherine's tweet and the coverage in the media and the political discussion, I'm reminded of a line from The Princess Bride, where in a wonderful scene, one of the lead characters says, "You keep using that word. I do not think it means what you think it means." And in my mind, I'm thinking the science. In fact, there is a real disconnect between what's in the reports and the scientific literature and what you hear in the political, the popular, and the media coverage of climate science. And so what I want to go through today for you is, first of all, talk about the consensus view, and I will try to use appropriately green font for that. We'll talk about detection, attribution, and models, and projection, and I will intersperse that with, perhaps appropriately in black font, some of the buts that give me and many other knowledgeable scientists pause as one discusses what the state of climate science is. We'll then go on to observed impacts and projected impacts, and hear almost exclusively from the reports themselves. And then finally, we'll talk about possible responses to the changing climate, and again, with a set of buts. Let me insert a caveat. This is a complex and nuanced subject. I could spend a whole term in a course talking about this. Obviously, in just an hour, we're going to have to sacrifice some completeness and also keep things pretty short. Nevertheless, I'll try to give you a sense of what I think is really going on, and of course what the reports actually say. So let's start about detection, and the reports will say that we've seen unusual increases in the global average temperature in recent years. And shown on the left there is a figure from the US report showing the global annual temperature of the globe from about 1880 to current. And you can see that certainly in the last couple decades it's gotten warmer. Overall, we've seen a rise of about 1 degree centigrade since the early part of the 20th century. That's also, as shown in the right-hand figure there, pretty uniform over the globe, with the poles warming more than the equators, as would be expected generally as the global temperature increases. There are other indications of changing climate. The atmosphere is warming, the oceans are warming, sea levels are rising, Arctic ice is shrinking, glaciers are shrinking, we see growing humidity, and so on. Well, all true. But in fact, maybe that's not so unusual. Let me go back for a second. If you just look at that left-hand graph, you can see that the warming is not monotonic. That suggests that there are other forces beside rising human influences that are driving the climate. And in fact, from 1950 to 1970, the temperature actually went down a bit. So there have to be other things involved. It's not just human influence. You can see also that it's not just human influence by taking these two sections of that same record. One of them is from 1957 to 2008, when human influence were operative and growing, and the other was from the early part of the 20th century, when human influences were much less, and presumably this is natural. And in fact, you can see if you line them up, it's kind of hard to tell the difference. And in fact, if you calculate the slopes of those temperature trends, 30-year trends, as shown on the right, you can see that the rate of warming in 1940 was just about as high as it was in recent times. So that's not to say that human influences are not operative at present in causing the warming and the changes we're seeing, but that that there are natural influences that are also operative, and you'd better have those under control if you're going to attribute what you see to human influences. Geological perspective is also interesting as you think about this. This is, as best we can put together, a record over the last 500 million years of what the surface temperature of the globe would look like. Note, by the way, the changing scale along the bottom. We came out of the last glaciation about 20,000 years ago, and the temperatures have been rising. You can see the little ice age way down there at the last little fraction of a millennium. And interestingly, again, basic Earth science, but not known or widely discussed, is that about 125,000 years ago, we were in the last interglacial, when the Earth was not covered a lot by snow and ice, and the temperatures then were 2 degrees warmer than it is now, and sea level was 6 meters higher than it is now. These variations are driven by the Earth's orbit. We sort of understand them, but again, just to say that there are powerful natural forces we had better understand if we're going to pin what we see on human influences over the last couple decades. All right, so attribution. Humans have caused at least half the warming since 1951, say the reports. And in fact, human influences, they say, are consistent with all the warming we have seen since 1951. Humans influence the climate by greenhouse gases. We'll talk about that. Aerosols, changes in land use, which change the reflectivity of the Earth's surface. And then natural influences include variation in the sun, natural and volcanic aerosols, and changes in the carbon cycle. And the basic argument is that, for pinning it all on humans over the last 40 years, is that there's no other cause we can think of that is responsible for the warming that we see. So let's see just how big human influences are and how they've changed with time. This is the record of carbon dioxide in the atmosphere over the last 2,000 years. And we see that spike in the last century or century and a half. That's clearly human. Okay? We are burning fossil fuels, and they are causing the atmospheric concentration of CO2 to go up from about 280 to the current 400 and a few right now, going up by about 2 to 2.5 parts per million per year. So what does that growing concentration of carbon dioxide do to the climate system? In order to understand that, you've got to look at how energy flows in the climate system. This is a picture again from one of the reports. And the thing to take away from this is, first of all, it's complicated. There are lots of arrows of flows of energy going on here. The big ones are that the solar energy comes in, about a third of it gets reflected, the rest of it is absorbed by the surface re-radiates that energy as infrared, some of it gets trapped in the sky and gets radiated down again, so up and back radiation flows, and eventually whatever you need to balance the input comes out as infrared radiation. Lots of pieces, numbers characteristic of about a couple hundred. The carbon dioxide influences this system by adding about 2.5 watts to these energy balance. So it's a relatively small perturbation on this complicated system that we're trying to understand, right? Less than 1%. Here are the different human influences, again from one of the reports. The biggest influence is carbon dioxide, which accounts for about 2.5 watts. There are some other greenhouse gases, methane, halocarbons, and so on, which are about another 1.5. Then there are some negative influences, aerosols that tend to cool the planet by about 1, and the net is, as I said, about 2.5, with pretty big uncertainties. So we need to understand how this 2.5 watts is changing the climate system in order to firmly attribute what we see to human influences, and of course to project what's going on out to the end of the century, let's say. Here is how it goes quantitatively over the last 250 years. Here are, again, influences. The human influences are the orange line, the net, total anthropogenic, and then volcanoes go off every once in a while and act to cool the planet, as we can see sometimes in the temperature record. The big thing to take away here is that before 1950, human influences were about 0.5 watt, and currently, as I said, they're about 2.5 watts and growing. So anything before 1950, we can pretty well confidently attribute to natural, and anything after 1950 certainly has at least a human component, if not a human dominance in what we see. Let me tell you a little bit about models now, which is another important tool in this business. If you want to model the climate, you've got to model the atmosphere and the ocean. And the way in which it's done is to cut both of them up into cubes, if you like, or rectangles, typically about 100 kilometers on a side in the best models now, so 60 models on a side, and many layers going up into the atmosphere and down into the ocean, let's say 20 each, and then use the basic laws of physics to move air, water, energy through the system, radiation as well, and then do it time step by time step, say 6 hours at a time over a couple centuries, both under natural variability and under external influences. This is one of the most challenging problems in computational science. The consensus reports will say the models are useful, but they're imperfect, and anyway, they're the best we got, and they're improving all the time. Those are relative statements, and the real question is, are the models good enough to be able to usefully understand and project? Whoop, we just lost it. The buts here is the models are not just physics. You will read in the papers, how could the models be wrong? It's just the laws of physics. Well, the answer has got to do a lot with what's called subgrid scale phenomena. I show you here a satellite photo. It's a real picture of the Gulf Stream peeling off from the Cape Hatteras. This is the temperature of the surface of the ocean. And you can see all of that wonderful structure. There are other structures in the climate system that happen on scales much less than the 100 kilometers of the grid boxes. And so you have to make assumptions about that because you can't treat it explicitly in the computer. For example, given the average temperature and humidity in a grid box, what are the clouds like? How many clouds are there? What altitudes are they? What fraction of the sunlight do they reflect? And that's an assumption. You can try to ground it in data, but it's as much art as it is science. And so putting these small-scale phenomena into the models, which are absolutely crucial, is something that is a big uncertainty in the models. And interestingly, the models fail to introduce important aspects of the climate, at least of the scale of the phenomena we're trying to understand. Some of the issues include subgrid scale parameterization of the clouds, as I mentioned, but also of convection. This little cartoon of what the model grid looks like is really misleading, because in fact the layers are about 0.5 kilometer high typically. The scale height of the atmosphere is only 5 kilometers or something like that. But the horizontal size is 100 kilometers on a side, and so they're really like pancakes more than they are like cubes. And that makes it very difficult to describe the vertical convection that's so important in the atmosphere, hot air coming up from the ground into the sky carrying water vapor with it, for example. The ocean initial conditions. We don't really know what the state of the ocean is 30 years ago. It's only in the last 10 years that we've had floating buoys that will dive down to a couple kilometers depth and measure the temperature and currents, salinity of the ocean. As I showed you, greenhouse gases warm the planet, but aerosol tend to cool, and you can build a model that's very sensitive to greenhouse gases and very sensitive to aerosols, or not very sensitive to either one. They'll give you the same answer currently, but give very different projections about what will happen over the next 100 years as greenhouse gases accumulate. And then finally, the climate system has long-term coherences in it that the models do not reproduce. Let me show you just how badly the models reproduce some aspects of the climate. This is the global temperature modeled over the last 100 and something years. The black line is the observations. The spaghetti lines are all of these different models that are used by the IPCC. And this is really misleading because, in fact, the average temperature of each model differs, as shown over here, by as much as 3 degrees centigrade. And they've all been adjusted to line up to 0 for the period 1950 to 1980. So in fact, when the models differ by 3 degrees, which is more than what you're trying to explain, it gives you some pause that you've got it right. All right. Multi-decadal variability is really important and is not in the models. Here's an example of something called the Pacific Decadal Oscillation. This is a real phenomena. You can see the two different modes as shown in surface temperatures here in one phase and then the other. And here's the actual temperature record from observations. This is a long-term mode in the system having to do with energy sloshing around in the Pacific Ocean. And there's a similar mode in the Atlantic called the AMO, the Atlantic Multi-Decadal Oscillation. The models do not have this at all. And so to the extent that these influence the climate system, the fact that your model reproduces it, but it doesn't have these variables in it, suggests that something is missing. So these generate uncertainties in how we go forward. The consensus shows you that figure on the left, which is the average of all of these many models compared to observations, which is the black, and they're happy that, hey, we got it about right. In fact, they're missing over here. We'll talk about that in a moment. And then they turn off CO2, and they say, look, it's clear that CO2 is what's causing the recent warming. Well, in fact, the models have been tuned, and so it's not surprising if you take out one of the factors, you're going to destroy the tuning. How badly do they do? I show you here the rate of warming for this region over here, actually for the whole run, and you can see that the observations, which are the blue line, warm at a rate that's up to 3 times greater than what the models show, and they're really not doing a very good job at all. So the models need to be taken with a grain of salt. And in fact, this earlier period, even the IPCC says it remains difficult to figure out what's causing that. We just don't know. And at least for many of us, until you've explained variability on all of the scales relevant to the alleged human warming, you haven't really nailed it down. Okay. Just one more example of model failure. This is satellite measurements of the temperature in the lower atmospheres, the black line, and the models are running too warm. Okay, I couldn't resist. Jeff in the audience is the author of one of the Indiana climate reports. This is the annual average temperature of Indiana in Fahrenheit, not centigrade, so divide by about 2. You can see a little bit of warming, but you see a lot of variability on the scale of the last 30 years and from 1940 to the present, which people think they have an explanation for, but maybe not. We've seen some changes in precipitation and a little bit more in the number of wet days or extreme precipitation events, but again, signal to noise is a problem. All right, let me turn to projection a little bit, and the consensus will say we can usefully project future climates. We need to assume future course for human influences. That means we need to make some assumptions about global demography, development, technology, regulation, and what are the greenhouse gas emissions and concentrations going to look like 100 years from now, aerosols, land use. The way that the consensus does this is to make scenarios called representative concentration pathways, or RCPs. We'll talk about 4 of them. They're labeled by a number n, where n is the forcing in watts per square meter in 2100. So if n is a big number, it means that the forcings will have grown greatly to the end of this century, where if n is a small number, it means we will have reined in the human influences. And then we take these forcings, we put them into the models, we run the models forward, and we project what's going to happen with the climate. And then we average over the ensembles of 40 or 50 different models. So here's some sense of what the RCPs look like. Here is, for example, assumptions about population of the globe in these different scenarios, 2.6 going to 8.5, and assumptions about global GDP going out to 2100. And then when you do that, you can extract annual carbon emissions. There's the 8.5, which has got high carbon emissions, and the 2.6 in which carbon emissions peak and then drop down. And of course, they all more or less agree with what we've observed so far, but then have different projections for what will happen in the future. And then you can run your climate models and get a change of what the global temperature will do going forward. And of course, the high emission scenarios, not surprisingly, show high temperature rises. Low emission scenarios show low temperature rises. I urge you for later discussion to note that one in which the temperature stabilizes at a rise of 2 degrees Fahrenheit by the end of the century has essentially 0 emissions by the end of the century. We'll discuss in a minute the plausibility of that assumption given demographics, energy needs, and so on. All right. Let me skip this one because I want to get on to impacts. The consensus will say that impacts are already bad and going to get worse, and they can tell you, if the temperature rises so many degrees centigrade, we're going to start seeing falling crop yields, we're going to see problems with water ecosystems, and so on. Essentially, the global temperature is used as a proxy for other impacts, and 2 degrees was alleged to be a safe limit. Now everyone's talking about 1.5 degrees, but it is still an ill-defined threshold. I once asked the guy who was responsible for the 2-degree threshold setting, why did you pick 2 degrees? Why not 1.5 or 2.5? This was about a decade ago. And he said, well, it's an easy to remember number, and it's about right. But it's a pretty fuzzy number. All right. So, what does the consensus say about impacts? It's kind of muddled. If you read the reports, the song goes something like this. For some climate observable X, storms, sea level, heat waves, they'll say X has changed in recent decades. Humans have influenced X. Our understanding of X has improved, which is a relative statement. The human impact on X is uncertain or not yet detected because there's natural variability, a poor historical record of the data, there are confounding influences, or the models are not in agreement. Nevertheless, human impacts on X are going to grow, but there are uncertainties in how much it's going to change, but nevertheless, it's going to get worse, invariably. And the degree of confidence in each one of these statements depend on what X we're talking about. It's really interesting to read the reports like this. Nevertheless, let me tell you what IPCC said about weather extremes. Since about 1950, it's likely that we've seen less cold days and nights, and the number of warm days and nights have increased, but only medium confidence that the number of warm spells has increased. It's likely that we've seen more heavy precipitation events in more regions than there have been decreases, but there's strong variation across regions. We have low confidence that there's any trend in floods on a global scale. We have low confidence that there's any trend in drought or dryness over the last 60, 70 years. We have low confidence that there's any trend in small-scale weather phenomena like hail and thunderstorms. We have low confidence in any centennial-scale changes in tropical cyclone activity, although we have seen an increase over the last 30 or 40 years in the strongest cyclones in the North Atlantic. We have low confidence in changes in the intensity of extreme mid-latitude storms, extratropical cyclones, over the last 115 years. Gavin Schmidt, who is the director of NASA GIS and is one of the preeminent figures in expounding the consensus, said, and I'm sorry, let me get this back to where it needs to be. Nope. So I need a little help, I think. How do we go back?
You just want to project
Yeah,
this.
just continue to project. Okay. All right. General statements about extremes are almost nowhere to be found in the literature, but seem to abound in the popular media. It is the popular perception that global warming means all extremes have to increase all the time, even though if anybody thinks about it for a little bit, they'll realize that that's nonsense. So, the media want to blame every storm, every flood, every drought on climate change, and it just isn't like that, even according to the official reports. Here's some data now from the National Climate Report. We're going to go through a set of extremes and what the reports actually say. This is the change in the coldest temperature of the year over the last 30 years relative to what it was in the previous 60 years. And you can see that the cold extremes have all gotten a lot less. The lowest temperature of the year have warmed. And if you look at the warmest extremes, hardly any change over the last 60 years. Half the country's actually gotten cooler, and the western half has gotten a bit warmer. So really what's happening is that the coldest temperatures are increasing, the warmest temperatures are not going up, at least for the US, which has got the best and longest meteorological records around the globe. So we're not seeing warming, but really a milding of what's going on. And agricultural intensification, which you folks know well in this part of the country, is certainly playing some role here. But some of it is clearly natural as well. Let me talk about sea level rise a little bit. Here's a graph of sea level from 1900 as determined by tide gauges. We've got a network of tide gauges around the globe. Their readings can be combined and try to get some estimate of what the global rising level of sea level is. And you can see it's gone up by about, I don't know, minus 100, 200 millimeters over about 100 years. So that's 2 millimeters a year on average. We have satellite measurements since the early 90s. It's quite a feat to take a satellite some hundreds of miles up and measure its altitude relative to the sea surface with a precision of less than a centimeter. They give you this kind of data. It's great global coverage, and we see again rates of rise that are commensurate with the tide gauges. What people don't understand generally, unless you understand earth science a bit, is that sea level has been rising for the last 15,000 years. This is the sea level as determined from the geological record. You see we've gone up 120 meters over the last 15,000 years. Very rapid rise as the glaciers melted from the last deglaciation, and then a much more gentle rise over here. And the real question is whether the rise that we're seeing over the last 50 years is attributable to human influence or not. The consensus documents show you this graph, which is over the last 2,000 years, and the last century is rising a bit faster than previous centuries. But what you really want to know is what's going on over the last 50 years, which is when humans are influencing the climate. That's shown in this graph, which you don't find in the assessment report. So rate of rise over 15-year intervals in millimeters per year over calendar year over the last century, ups and downs, big error bars, and some satellite numbers over here. So we're seeing in recent decade some acceleration, but I would argue, and I think many other people would argue, within the bounds of natural variability, what we have seen before. What makes this? Nobody really knows. Let me not go through those numbers. What it would take to convince me is at least a good explanation of the prior variability and something more than a 1 or a half a sigma signal. Not there yet. Let's look at projections of sea level rise for a little bit. This is again from the US government report. Here are the tide gauges, this is sea level, and various scenarios. Okay. I'm again a data-driven guy, so I go look at the tide gauge in the battery. This is NOAA data, the tide gauge at the tip of Manhattan that's been running for the last 150 years. Pretty good straight line at a rate of 2.8 millimeters a year. If we were to get a 1 meter rise in sea level, which is over here, the blue line, by the end of this century, this line would have to go up at an average slope indicated by the green line for the rest of the century. I don't think that's going to happen. Okay? Not certain, but it sure looks discordant with what we've seen for the last 150 years. Hurricanes. This is the record of hurricanes from 1980, so about almost 40 years worth of record. This is the number of hurricanes over the globe and the number of major hurricanes over here. Hurricane activity, which is what's called the accumulated cyclone, cyclonic energy, ACE, for global and northern hemisphere. This is the number weighted by the square of the velocity of the hurricanes. You look at those graphs and it's hard to see a trend. And in fact, The report says there's still low confidence that any reported long-term trend in hurricanes. Even better is this statement from a government website, NOAA. It's premature to conclude that human activities, particularly greenhouse gas emissions, have already had a detectable impact on Atlantic hurricane activity. Lest you think that that's the current administration putting its finger on the scale, I would note that this was posted in the spring of 2016. Nevertheless, if you get all your climate information by watching CNN or reading the New York Times or the Washington Post, this is a surprising statement. Sea ice, we're running out of time. I think I want to go on and skip that one. Let me talk about agriculture just a little bit. The reports say agriculture is going to crash. All right. But in fact, if you look at the data, this is NASA data, the leaf area index, how green the planet is, has actually gone up by about 30% over the last 30 years. Most of that, says NASA, 70% of that increase is due to CO2 fertilization. Plants love CO2. They need other things to grow too, but on average the Earth has gotten greener because of atmospheric CO2 levels. And crop production, despite the rise in temperature and so on, is just going gangbusters. This is world grain production over the last 50 years, I guess, and keeps going up. We're pretty good at growing food. All right, one more on impacts, and then we'll get to what we can do about this. If you read the report, here is the impact on US economy in 2090 relative to today as a percentage of GDP, depending on how much the temperature rises. All right? And for, let's say, a 4-degree rise in temperature centigrade, 8-degree Fahrenheit, we're looking at about a 4% impact in US GDP by 2090. Similar figure for the global economy, temperature increases of a few degrees, 3 or 4, impact of about 3 or 4% at the end of the period. When this came out, just after Thanksgiving, the headlines in all the media were, the climate's going to crash the economy. Well, if you think about it for a little bit, it just ain't so. And let me show you that. I put a piece in the Wall Street Journal. This is at worst a bump in the road. This is the actual data on US GDP growth. Since 1930, we've gone up by a factor of 20. The percentage annual growth rate in real GDP averages 3.2%. So let's assume conservatively that we'll see 2% per year average growth out to 2090. 2% a year for 70 years is a factor of 4. All right? So in fact, the projections for the US economy under relatively modest assumptions are that blue line. If you say there's going to be a 4% hit in 2090, you get the orange line. And you say there's going to be a 10% hit by 2090, you get the gray line. So in fact, at most, the 10% decrement is a delay in growth by 5 years. The $550 billion number that was in the report and in the media is 0.6% by 2090, or 4 months delay. So if the report had said instead, we will delay economic growth by less than a year when the temperature rises by 3 or 4 degrees centigrade, I think the discussion would be a very different one in the political and policy circles. They don't tell you that. We can get into why they don't tell you that, but at some level that's above my pay grade. I'm just a scientist, all right? I just do numbers. What are we going to do about this? And let me just spend a few minutes talking about that. There are 3 ways of trying to deal with this problem. One is mitigate human influences. Let's reduce them, largely by reducing human emissions of greenhouse gases. We can adapt. changes in infrastructure, changes in processes, the kind of crops we grow, for example. Or we can geoengineer, we can intentionally intervene in the climate system. Which of these we do is really, in part, a quantitative question. What's the cost? How effective are these? What are the collateral benefits or detriments? What is the perception of them? And ultimately, how much we do is a values judgment. You can't tell the political system how much risk to take or how to balance economics versus development, environment versus development. That's not a scientific discussion, but I think we scientists can at least portray what the likely consequences are of one or another decision, and that's really our job. Let me skip this. Greenhouse gas emissions are rising. These are global emissions. As you can see, let's say before this century, most of the emissions were coming from the developed world, and recently China has become a big player, and India is not far behind. So going forward, most of the emissions will come from the developing world, but most of the emissions have come from the developed world. The damnable thing about trying to mitigate is that carbon dioxide lives in the atmosphere for hundreds, if not thousands of years. And the story, this is slightly out of date, but it illustrates the principle. We're putting, these days, about 35, 38 billion tons a year of carbon dioxide into the atmosphere. About half of it gets absorbed by the oceans and the land, and the other half stays in the atmosphere, and so it's just accumulating. That simple fact has profound implications for how easy or hard it's going to be to reduce human influences by reducing emissions. And let me show you that. The cumulative emissions, which is what we need to really worry about, are this black line, all right? This is real data, cumulative CO2 emissions up to the present. So let's look at the emissions. We can make a cartoon. It looks something like that over time. And the concentration, which is the integral of the emissions, since it just accumulates to within a factor of 2, is going to look like that. Let's suppose that we manage to make some reduction in emissions, like that, 10%, 15%. Then the concentration is going to do that. It still keeps going up, just doesn't go up as rapidly. And if you think that the danger line in the concentration that you shouldn't get above is at some level, I chose 600 parts per million here, you can see what you've done is to delay but not prevent the concentration from going up. If we really want to reduce human influences, you've got to make drastic reductions in emissions. And here again from the consensus, it shows different emissions trajectories and the different radiative forcings that result. And you can see if you just want to stabilize human influences, let's say at the green line, you've got to drive the emissions to 0 or below by 2070. 2070 to stabilize at 2 degrees, 2050 to stabilize at 1.5 degrees. So that means, you know, no oil, no gas, no agricultural emissions, which are 25%, no coal, absent sequestration or biological offsets. Let's see how plausible that is. This graph is a little bit out of date also, but illustrates, we plot GDP per capita for different countries and the emissions per capita. The US is up here, pretty high, but actually going down by about 10 to 15% over the last 2 decades. European countries in the middle, but there are all these countries down here whose trajectories are pretty much universal, and with emissions growing as these folks develop. And so, in fact, the real problem is how do you reduce the emissions up here, but more importantly, there are like 6 billion people down here. How do you rein in the emissions from these countries? Given that fossil fuels are cheap, readily available, and easy to use, and currently supply 80% of the world's energy, it's kind of hard to see how we're going to go to 0 in 30 years or 50 years. Today's global average is there. If you want to stabilize, you got to get down there. below the level of India. Okay. I just do numbers, right? Okay. Paris Agreement. This is the emissions trajectory historically. The gray line. In Paris, each country gets to pledge certain reductions. And each country got to determine on its own the intended nationally determined contributions, the pledges. If all of the countries fulfilled their pledges, we'd get down to the yellow lines, yellow bars. Not to zero, just bending the curve just a little bit. All right. I remind you that Paris has 5-year reviews with self-reporting, no enforcement mechanism, and is not binding. The most recent look says that the US, EU, and Japan are not going to meet their 2030 commitments, wherever they committed up here, without further policy changes. Whereas China committed only to peak its CO2 emissions 10 years from now. They seem to be on track to doing that, but who knows, right? They're still going up. And never mind about India, Indonesia, and so on. All right. So I look at this, and my sense is that adaptation is what the world is probably going to do. Whether it will do or not, it's a value. It will do what it should do is a values judgment. Adaptation is agnostic. It doesn't matter whether this is a natural change or a human-induced change. It's proportional. We will adapt more if the climate is changing more, and less if the climate is changing less. It's local, and so it's politically palatable. You're not asking people to make sacrifices for something a couple generations away and halfway around the world. It's also autonomous. It's what society does anyway, and it's going to happen on its own. It's also effective. But adaptation is much easier if you're richer, and most of the world is not particularly rich. It's also much easier if you know what you're adapting to, and the models are not good enough to be able to tell us what's going to happen, other than that, let's say, sea level is going to keep going up, but we sort of know that already. So, my key takeaways, and these are descriptive statements, not normative yet. Climate is going to continue to change under natural and growing human influences. The consensus that it's all human-driven recently is not as solid as popularly perceived. Beyond rising temperatures, most projected impacts have not clearly emerged, and I showed you some of the report statements about that. And we're unlikely to even stabilize human influences by the end of this century, and adaptation will be the dominant response. Let me close, since I try not to be normative, because I don't think scientists should do that. You should lay out options. But often people ask me, if I were in charge, what would I do? And so I will violate my rule a little bit. First of all, I would clarify the climate science discussion and, the climate policy discussion and the science that underlies it. We need better and continuous observations of the climate system. We don't do a very good job at that. I would reframe the discussion as a values discussion under scientific uncertainty. And as some of you may know, starting already a year and a half ago, 2 years ago, I was advocating for a red team that would scrub the consensus reports and ask the hard questions about it, both to make sure that we have integrity in the scientific input and also to ensure that we've got a good picture of what the system is actually doing. If you follow the news, you will have read recently that that idea is gaining some traction in the White House, and perhaps we will actually get to do that and paint a clearer picture of what the reports actually say. It's obvious we should pursue the easy emissions reductions, which have many collateral benefits. The non-CO2 greenhouse gases, leaking methane, for example, cost-effective efficiencies, again, a no-brainer. I would electrify transport. It's sort of happening already for the light-duty vehicles. We should encourage it because it has collateral benefits. And I would do our research, development, and demonstration for low-cost emissions-like technologies. Fission, small nuclear reactors. Fission generally has got to be part of the picture if we think we're going to reduce emissions. Storage, grid management technologies, solar, et cetera, et cetera. I would reduce emissions further mandatorily if and when the science becomes more certain, the signal comes out of the noise, which it has not yet, a values consensus emerges, or the zero emissions technologies become cheaper than the alternatives. And I would pursue adaptation rigorously. There's a lot of science or academic work to do here to understand the different modes of adaptation, what works where, the relative costs, and so on. So I think we spent a lot of academic time on mitigation. I think we need to focus more on adaptation. And I would investigate geoengineering as a last resort. It's not something to be deployed now or perhaps ever, but we need to know whether we have that option in our pocket should the need arise at some point in the future. And with that, I see I've got about 5 or 6 minutes left for questions and comments. I hope there are some, and I'm happy to respond. Thank you.
Thank you so much, Steve, for a fascinating tour of our current understanding of the science of climate change. So, any questions from the audience? I'm sure there are plenty of them. Okay, any questions? Vlad, I see you there.
So you mentioned that many times how the current models are actually most efficient. But with all this recent improvement in terms of big data processing, machine learning, AI, do you see any improvement in this modeling?
Yeah, so just to repeat the question, because you don't have a microphone. I talked a lot about the deficiencies in the models. Do I see any potential for improvement using big data, AI, the more modern technology, information technology? And I think there is some promise there. There are people who are investigating AI methods for nailing down the subgrid scale parameterizations. So I take all the data about how many clouds are observationally in a given cell as a function of temperature, humidity. Can I use AI to build a better subgrid scale model? I think absolutely. It's like a lot of areas of simulation. The big simulations generate an enormous amount of data. And using AI or machine learning more generally could well be a tool to help us extract information better from the models. One of the big problems with the models is just trying to understand which models are better than others. And you can make a list of 30 different observables and 50 different models, and some do better on some things and some do better on other things. And just trying to understand which ones you should believe for what is a challenge. So yeah, I think so. And people are trying to do that. There's an effort at Columbia, there's an effort out of Caltech to do AI like that.
I mean, I think, Vlad, in addition to that, we are fielding larger and larger supercomputer machines, exascale type computers in the Department of Energy, and I think that's, together with AI machine learning type algorithms, is going to help sort out.
It will help, although let me again quote, I love sobering facts, all right? Yeah. So if you decrease the scale length from the current 100 kilometers, let's say, by a factor of 2 or whatever, the number of voxels goes up by the cube. So, and then the time step has to be smaller, since you can't take bigger time steps to move the stuff more than 1 voxel, the Courant condition, as it's called. So the computing time actually goes up as the 4th power of the spatial resolution, at least, maybe more. And so if you want to go from, let's say, 100 kilometers to 10 kilometers, I need 10,000 times more compute power. It'll be a while till we get to that.
Good. Other questions? Yeah, Martin.
You've talked primarily about the temporal variation on a global average. Could you comment about spatial variations at a given time?
Yeah.
Are there parts of the world that will be more impacted or less?
You can show from quite general physical arguments that the poles will warm faster than the equator or than the tropics. And there was a headline in, I can't remember, CNN or something last week, Canada is warming at 2 to 3 times the global rate. Well, duh, that's just sort of basic physics, all right? The tropics probably won't warm all that much, but what is more interesting is the vertical profile of the warming. It doesn't affect us much directly because we live on the surface, but it is a signature of how well we understand the energy and moisture transports in the system. Remember, we're looking at 1% effects. And in fact, a persistent problem is that the modelers show what's called the tropical hotspot, which is warming at about 30,000 feet over the tropics, whereas the data don't show that at all, by a big factor. And the modelers keep saying the data's wrong, and the data guys say, look at the models, you know, you're warming at 3 times the rate that we see. So we don't understand everything at all about this. It's a difficult business.
Rosie?
Thank you for your talk. I enjoyed it. I have a couple questions. One is about how much your critique is really about the scientific reports versus the media coverage of those reports. And then, you know, certainly you referred to media coverage at times. Do you have evidence about that media coverage? It seemed, you know, I'm a political scientist, so I want to see data on the actual media coverage and whether it's doing some of the things you're saying it's doing.
Let me talk about the critique first. You know, a lot of the reports are right, but obviously I would not be urging a red team exercise unless I thought that there are misleading crucial aspects of the reports. What I'd like to say is I believe, to be determined, that they are written more to persuade than to inform. And, you know, having 30 years experience in providing advice to policymakers about science, that's not where we want to be. Okay? It's okay to write an advocacy document, but not with one bearing the mantle of science. And I believe the reports have that problem. Okay? On media coverage, I find it really hard to find. I look at a lot of different media sources, Washington Post, Wall Street Journal, New York Times, CNN, and I can't find, it's hard to find realistic coverage. And you know, how much of that has an impact, I don't know. Okay. I mean, how much of any of this has an impact on public opinion, I don't know. But again, my job, and I think the job uniquely for scientists, is to lay out the science accurately, completely, transparently, and self-consistently. And we haven't done that, I think.
Suresh?
Steve, thank you very much for the talk. This may not have been the focus of your talk, but going back to Martin's question about spatial variation, any changes due to climate change are exacerbated by the population increase and by the localization of population increase. So, you know, water shortages, wars, many other things. So I'm curious if you've seen a good study of impacts from that point of view, that even if it's 1 degree or whatever it is, ultimately there might be extremely concentrated effects in some parts.
Right. So, this is I joked to Larry Summers a couple months ago in a conversation. This is a doubly dismal science, all right? Because first of all, you've got climate science, which, as I've tried to show you, is pretty complicated in and of itself, and I'll come back to an example in a moment. But then on top of that, you're going to lay economics or human behavior, which is equally difficult to do. So you're compounding the two when you start to get into issues of the kind you raise. Let me just give you one example of how dismal the climate science is. 2 years ago, we saw the end of a severe drought in California. And all of the headlines said, this is exactly what the climate models predict, and you see it's happening. And of course, we've seen now 2 or maybe 3 years of record wet in California. All right? And then, of course, you start to see the papers now that say this is exactly what the climate models predict. So I think when you get to try to do predictions on a regional scale, it's really difficult. You saw how across the board the global predictions are already in terms of sensitivity. When you get down to regional scales, the noise is even greater. So I don't think we know. I think the best thing you can say to prepare is that we need an adaptable society. That means strong governance, strong economy, and those are probably the best ways to prepare for whatever nature throws at us in the future.
See, there's another question. Yeah, go ahead.
Yes, I just was trying, thank you, I thought your talk was very interesting.
Thank you.
And informative. I'm just trying to understand, I
Yeah, so let me, just one, at least clarification, all right? One of the problems in the popular discussion is that people use the word climate change to mean only human-induced climate change. And in fact, you can't blame them because that's what the IPCC, the UN body, defines as climate change, as only anthropogenic climate change. But I have shown you that the climate is more than capable of varying on its own. And so are you asking about human influences, or are you asking about a changing climate, which includes all of the above? Both. Who knows what scenario is going to come to pass in the future? First, so you have the uncertainty of how much emissions will grow in population, but you also have uncertainty in how the climate system will respond to the rising human influences. That is currently uncertain, again, according to reports, by a factor of 3. So if you were to double CO2, hypothetically, the system could go only up by 1.5 degrees, which would probably be net beneficial, or it could go up by 4.5 degrees, which would start to have impacts. But even if you saw the worst case, at least for the US, as I showed you, the economic impact is in the noise. Now, you can disbelieve the economic models, take them with a grain of salt, but it does not look, at least according to reports, like this is going to be a big deal economically in aggregate. We'll see differential impacts across the country, but the reports say 3 months of economic growth in 2090. Not much.
Okay. Any other questions or comments? If not, please help me thank our
Thank you.
speakers.
Thank you.